Linear algebra is an entire branch of mathematics that studies vector spaces and their linear operations. We have already learned the basic operations to do with vectors, but it's time we go beyond seeing vectors as simple geometrical arrows. They can be much more. In this video, we will first learn the required concepts that are needed to begin understanding vectors with an arbitrary number of dimensions. Before we look into n-dimensional vectors, let's first really understand what's going on in the usual two dimensions. And let's introduce an important technical term, a vector basis. So here I'm showing a vector v in a two-dimensional plane. Now when we write about this vector, we write it as a column vector, for example v equals 2, 3. And what we mean by that is that we have defined our two unit vectors, x hat and y hat, and then we are basically saying that our vector v is equal to twice the x hat vector added to 3 times the y hat vector. And in this way we can describe any vector in the plane. This means that what we usually called vector components can be defined as the scalars acting as coefficients for each of the basis vectors, in whatever basis we have chosen. This basis, x hat and y hat, is the only example of basis that we have come across, together with its three-dimensional version, x hat, y hat, z hat. But there are many more possibilities. For instance, I may choose a different set of two vectors as my basis. For example, let's consider these two vectors, e1 and e2. Now, in the same way that I could describe vector v as twice x hat plus 3 times y hat, I can do the same but using multiples of vectors e1 and e2. So I can describe vector v as 1 time e1 minus 2 times e2. And that's perfectly valid, and I can do the same for any other vector in the two-dimensional plane. For example, now I have 1.5 times e1 minus 0.5 times e2. But let's go back to our original vector v, because this is interesting. This means that if we are using our basis e1 and e2, then we might as well write vector v in component form as 1 minus 2. Right? Because we are multiplying the first basis vector times 1, and we are adding the second basis vector scaled by minus 2. Completely analogous to when we were writing the components as twice x hat plus 3 times y hat. So we have come across a very important thing to realize. One thing is the vector as an entity. This vector v has a certain magnitude and a certain direction. It is independent of which basis we choose to describe it. And another thing is the vector written in terms of its components. So that's either using the xy basis, so it's the vector 2, 3, or using this new e1, e2 basis, so this is the vector 1 minus 2. Notice that the same entity can be written in different ways using different bases. The use of different bases is like the use of different languages. One same concept can be written in different ways using different languages. And similarly, one same vector can be written in different ways using different bases. Now, with this choice of basis vectors, e1 and e2, are we limited in some way? This basis is certainly a bit inconvenient due to the different sizes between e1 and e2 and the weird angles that it has between them. However, using this basis, all possible vectors in the two-dimensional plane can be reached by a linear combination of these two vectors, e1 and e2. Now, this idea of combining two different vectors to reach any point in space is very important, and is related to a new technical definition that you need to be introduced to. The idea of the space spanned by a set of vectors. Consider all vectors that can be reached via a linear combination of a set of n vectors. Let's call them v1, v2, v3, all the way up to vn. This can be compactly written as the span of vectors v1, v2 up to vn. For example, we have just seen that the space of all possible vectors in two-dimensional space, which we may denote by the symbol v2d, is given by the span of vectors x hat and y hat. We have also seen that the same space, v2d, can be reached using linear combinations of the two basis vectors e1 and e2 from the previous example. Therefore, these two different bases are said to have the same span. To be more mathematically explicit about it, we can formally define the span of vectors v1, v2 up to vn as the set of all possible vectors v which can be written as a linear combination of the vectors v1, v2, vn. That is, any combination of the vectors with all possible values of the scaling coefficients. Consider more examples. The space of all of three-dimensional space, v3d, can be defined as the span of vectors x hat, y hat, z hat. Also, a plane that is given by the parametric equation r equals alpha u plus beta v can be compactly referred to as the span of vectors u and v. As a curious thing to note, this plane is a plane that includes the origin. Indeed, the origin is always included in the span of any vectors, because you can always make all coefficients equal to 0. Now, let's look at examples of span in a more visual geometrical context. Let's consider what is the span of a single vector e1. Using the definition of span, it's the set of all vectors v which can be written as a linear combination of e1 only, that is, v equals lambda e1. This is exactly the parametric equation of a line crossing the origin, as we already know. Varying the parameter lambda, we can get any vector along the line. Therefore, span of e1 equals the line L. Now what happens if we add another vector e2? What is the span of e1 and e2 together? It's the set of vectors v that can be written as a linear combination of e1 and e2. V equals lambda e1 plus mu e2. This is our well-known equation for a plane, and we know that this span is the whole two-dimensional space. But can we prove it? A visual way to see it is to imagine lambda as if it was taking all of its continuous range of infinite values simultaneously, producing the infinite line L. Then, by sliding the value of mu, we are displacing this line in the direction of e2. Therefore, the addition of e2 allows the line to sweep across the whole two-dimensional space. We can also prove it analytically. For example, we want to prove that any vector v in two-dimensional space, which can be written as xy for any value of x and any value of y, can be also written as a linear combination alpha e1 plus beta e2. Looking back at vectors e1 and e2, we see that the first is the vector 2, 1, and the second is the vector 1 minus 1, so we can substitute this. Now, combining these two equations, we can write the system of equations x equals 2 alpha plus beta, y equals 1 alpha minus beta. So we need to find the values of alpha and beta that satisfy this equation for any value of x and y. Later in this course, I will teach you rigorous ways of solving linear systems of equations. But for now we can use the usual way that you have practiced in the past by adding and subtracting equations. So for instance, adding the two equations, or adding the first one minus 2 times the second one, we arrive at these two, from which we can obtain alpha and beta for any value of x and y. Therefore, this proves that indeed we can reach any point in two-dimensional space by a linear combination of e1 and e2. At this point, it may seem that the span of any two vectors will be the whole two-dimensional space. But that is only true if vectors e1 and e2 are linearly independent. This is an important technical concept that we need to learn. I will define it formally afterwards, but let's see it demonstrated visually with an example. What if vectors e1 and e2 are parallel to each other? Well, then We are kind of trapped in this line, right? No amount of varying lambda or mu will let us break free of this line. Therefore, in this example, the span of E1 and E2 is equal to the span of E1 equal to the span of E2 equal to the line L. Either of the two vectors is redundant in terms of calculating their span. This is unusual because having two vectors, and therefore apparently two degrees of freedom, lambda and mu, we can only span a single one-dimensional line. This happens because the two vectors are said to be linearly dependent. And how does this look numerically? Can we prove that we cannot reach any point in two-dimensional space using these two vectors? Let's proceed similarly to what we did before. We want to check whether any location v equals xy can be reached via a linear combination of two vectors e1 and e2. In this case, the two vectors are parallel, and so they are scaled versions of each other. If we try to solve this system like we did earlier, we will see that the system does not have a solution in general. It has a solution only if y equals minus a half x, which is precisely the line spanned by the two parallel vectors. So everything checks out. But thinking about it again, how did this happen? We are considering an equation of the form v equals lambda e1 plus mu e2. As far as we know, this has always been the equation of a plane. We have two parameters, lambda and mu, which are our two sliders. We previously studied that the number of free parameters determines the dimension of the space, and here we seem to have two. So why does the resulting linear combination have only one dimension? We just proved it analytically in component form, but we can also prove it more elegantly in parametric form. The problem is that lambda and mu are not really two different sliders, because they can be combined into a single slider. We simply have to notice that E1 and E2 are parallel. In this specific example, E2 happens to be twice E1. So let's substitute this into our parametric equation. V equals lambda E1 plus mu times twice E1, which we can now group as lambda plus 2 mu times E1. And now notice that if lambda and mu can both take any real value in the infinite number line, then the combination lambda plus 2 mu can be seen as a single coefficient that can also take any real value. So we can promote the expression lambda plus mu to be a new parameter. We can rename it as a new single coefficient lambda prime. So the two sliders have actually been combined into only one. And that is why this linear combination of two vectors only really has one single free parameter, only one degree of freedom, and so we can form only a one-dimensional line. Remember, this all happened because E1 and E2 were linearly dependent vectors. In two dimensions, this simply means that the two vectors are parallel. Things get more interesting in three dimensions. Consider the span of two vectors E1 and E2 in three dimensions. If these vectors are not parallel, they will span a certain plane. Now let's add a third vector E3. In general, this third vector will usually lie outside of the plane, and therefore this additional degree of freedom allows us to move this plane, sweeping it across the whole three-dimensional space, similarly to how we swept the line in two dimensions. Therefore, the whole three-dimensional space V3D equals span of E1, E2, E3. It makes sense. Three vectors span a three-dimensional space. This happens because E1, E2, and E3 are linearly independent, a concept which I will soon formally define. But what if the third vector E3 is not pointing outside of the plane? Then, any linear combination of E1, E2, and E3 will only allow us to travel across the plane, but not out of it. In this case, the vectors are said to be linearly dependent, and their span is equal to a two-dimensional plane. When three vectors span a two-dimensional space, this means that at least one of the three is a linear combination of the other two. And so it is a redundant vector, because we could span the same space without it. Finally, there is another scenario. What if the three vectors are all three parallel to each other? In this case, the span of the three vectors is equal to the line that contains them. No amount of linear combination of the three vectors will let us break free from this line. Once again, these vectors are linearly dependent. In this example, the span of three vectors is covering a one-dimensional space, a line, which means that at least two vectors in the set are redundant. We could span the same space by having only one of them. Mathematically, we could say there is even a third case. If all three vectors are equal to 0, then their span is simply the origin, a zero-dimensional space. In summary, we have seen that when we consider three different vectors, the span can either be a three-dimensional volume if the vectors are linearly independent, or a space of dimension lower than 3 if they are linearly dependent. So now that you have visually seen examples of linear dependence and independence in 2D and 3D, I think you have a clear intuition for what they are, and we can look at the formal definition in a general n-dimensional case. Let's start with linear dependence. A set of vectors v1, v2 up to vn are linearly dependent if and only if any of them is a linear combination of the others. For example, imagine that the last vector of the set, vn, can be written as a linear combination of the others. It is important to realize what are the implications of this. Consider the span of the set of vectors. If it turns out that Vn is a linear combination of the others, this means that the others can be added together in some way to produce Vn. And then Vn does not provide any additional degree of freedom to the span. The span is the same with or without Vn. Any location that can be reached by adding multiples of this vector Vn could have been reached anyway with linear combinations of the others. We may prove this analytically. This is a very similar proof to the specific example that we did in 2 dimensions, but here we are extending it to n dimensions. We start with the known definition of the span. The span of v1, v2, all the way up to vn is equal to the set of all vectors A such that A is a linear combination of the set, for all possible values of the coefficients a1, a2 up to an. Then, substituting the condition that vector vn is linearly dependent on the others, we arrive at the following, which we can rearrange as if we rename these sums of coefficients as a1', a2', and so on, we notice that this is simply a linear combination of vectors v1 up to vn-1, not including vn. But the set of vectors v that can be written in this form is exactly the definition of the span of the set of vectors v1, v2 up to vn-1, not including vn. So we have analytically proven that the addition of vector vn is redundant in terms of the span. The scalar coefficient an, which can be seen as a parameter that was supposed to provide us with a new degree of freedom, was lost. It was diluted into the other parameters, thanks to being able to write vn as a linear combination of the others. The new linearly dependent vector did not add a new dimension to the space spanned by the set. Now, back to our definition. This notation of writing vn as a linear combination of the others is giving unnecessary importance to the last vector of the set, vn. It may be that vn is not a linear combination of the others, but instead one of the other vectors is. The definition of linear dependence says that if any of the vectors can be written as a linear combination of the others, then the whole set is linearly dependent. So we should write the condition more symmetrically. We can do it by moving all terms to one side and leaving 0 on the other. So we can write that a set of vectors is linearly dependent if and only if alpha times v1 plus beta v2 plus all the way up to sigma Vn equals 0. If this has a solution apart from the trivial one of setting all coefficients to 0, then the set of vectors are linearly dependent. Next, let's look at linear independence. Linear independence is simply defined as the alternative to linear dependence. A set of vectors are linearly independent if and only if none of them can be written as a linear combination of the others. So we can say that alpha v1 plus beta v2 plus all the way up to sigma vn is not equal to 0, except for the trivial case when all coefficients are 0. In a set of linearly independent vectors, every single vector is linearly independent from the rest. Each vector contributes a new degree of freedom to the set. Each one provides an additional dimension of the space. Therefore, we arrive at an important result. If a set of vectors are linearly independent, the number of dimensions of the space they span is equal to the number of vectors in the set, n. For completeness, we can add back in linearly dependent sets that the number of dimensions of the span of a linearly dependent set is smaller than n, that is, at most n-1. We saw all the possible cases in 3 dimensions previously. With this new language, we can also give now a formal definition of a vector basis. A basis for a space V is a given set of linearly independent vectors which span the space V. Therefore, every vector living in space V can be expressed uniquely, which means in only one single way, as a linear combination of the basis vectors, whose coefficients are referred to as vector components in that basis. So, for example, in 2 dimensions, any pair of linearly independent vectors, E1 and E2, will be a successful basis for the 2-dimensional space, so that any vector can be written as a unique linear combination of the other 2. Notice that we can choose any 2 vectors which are linearly independent. The only problem comes when the 2 vectors are linearly dependent, in which case this is no longer a valid basis and we cannot describe vectors in 2D space by a linear combination of them. At the start of this video lecture, I promised we would see new ways of interpreting vectors, but so far we haven't. Before I introduce them, I wanted to build the necessary mathematical language. Look, for example, at our last definition. It's full of new terms: basis, space, linearly independent, span, linear combination. These concepts are the foundation of linear algebra, and it's important that you gain a solid understanding of them. Once you are familiarized with all these concepts, especially by doing exercises, these definitions should feel natural and almost self-evident. So let's summarize what we have learned so far using all this new vocabulary. We define a basis as a set of n linearly independent vectors. We define the associated vector space as the span of the basis. And we know that this space has a number of dimensions equal to the number of basis vectors, because they are linearly independent. Given a basis, every vector in the space is a unique linear combination of the basis vectors. So we can write vectors as an ordered list of its components. The components are simply the coefficients for each of the basis vectors. A different choice of basis might give us different components describing the same vector. And I'd like to add an important note on notation. So far, I have always tried to write things explicitly, such as when I have written V equals A1 E1 plus A2 E2 plus ... plus AN EN. But you really need to get used to reading and writing this kind of equation using the summation symbol. V equals sum from little n equals 1 to big N of coefficient an scaling the basis vector en. This is important because almost every book in maths and physics will give its definitions and proofs using this notation. This notation for vectors will be everywhere when you are studying things like quantum mechanics. On the next videos, we will make use of all the concepts that you have learned in this one and we will study fascinating examples of n-dimensional vector spaces.